So as we've been discussing, Hardy-Weinberg equilibrium is a predicted distribution of genotypes. And it's a distribution of genotypes that's predicted from the allele frequencies in the population. So in the past example that we were looking at, we had a population with these individuals with these different genotypes. We calculated the frequency of the big A allele, we calculated the frequency of the little a allele, and then we used these alleles and the probability calculations that we did in the last segment to arrive at this distribution of genotypes that we would be expecting in this population. So Hardy-Weinberg equilibrium is a predicted distribution of genotypes based on allele frequencies. And as we mentioned before, the reason why we can use allele frequencies to predict genotype frequencies in a population in Hardy-Weinberg equilibrium is because certain assumptions are met for this population. First off, that mating is random, that each genotype has the equal ability to survive and reproduce in this environment, so equal fitness. Fitness is just a technical term for reproduction capability. Something that we didn't mention before but should mention is Hardy-Weinberg equilibrium requires a large population. And the reason for this is in small populations, chance effects can dominate and shift allele frequencies from one generation to the next. Say, for example, if we had a really, really tiny population, say with only 4 or 5 individuals, just based on chance, you could have disproportionate matings that are non-random, essentially. Basically, you could have it just by chance that all the little a individuals interbreed with each other, just because there's so few mates to select from. So those kinds of effects can predominate in a small population, but in a large population, it's averaged out, such that we have random mating. And we also mentioned that there's no mutation, or the assumption is that there's no mutation and no migration. So there's not a large number of individuals coming into the population or leaving the population, which again would shift allele frequencies from one generation to the next. So if these criteria are met, then a population will be in Hardy-Weinberg equilibrium, which means that allele frequencies from one generation to the next will not be shifting, and that allele frequencies can be used to directly predict genotype frequencies. There is what's called a Hardy-Weinberg equation, which we can now discuss. The Hardy-Weinberg equation is simply the mathematical description of how we use allele frequencies to predict genotype frequencies. If we define the frequency of the big A allele as P, and we define the frequency of the little a allele as Q, then we expect, for a population in Hardy-Weinberg equilibrium, we expect P squared big A individuals. If you go back in the last segment and look at how we calculated the frequency of the big A class, you'll remember that we said, okay, reaching into the population, modeling it as a jar of marbles, we need to reach in and find a big A, probability 0.6, and another big A, probability 0.6. Well, 0.6 times 0.6 is P squared, and then this is just a way of representing that. We expect P squared big A individuals. Similarly, we expect Q squared little a individuals, and that was just 0.4 in that example, and 0.4, which is Q squared. The heterozygous class, as we worked out in the last little segment, we expect 2PQ of those. Okay? So we discussed how, say, we reach in, and for the female gamete, we get the big A, and then we reach in and get the little a gamete for the male gamete, and then we would say or, and then the other way around. That's where this 2 comes from. And the P and the Q is just the frequency of these multiplying together. So we expect 2PQ, big A, little a individuals. We expect P squared, big A individuals. And we expect Q squared, little a individuals for a a population, that's in Hardy-Weinberg equilibrium. Now, not all populations are in Hardy-Weinberg equilibrium. Anything that doesn't meet those requirements that we talked about can take a population out of Hardy-Weinberg equilibrium. And in the next segment, we'll start to look at a population where that's the case. So let's examine a population that is not in Hardy-Weinberg. Any population will have a P and a Q value. These are just the frequencies of the various alleles. So if P is equal to the frequency of, say, the big A, Q is the frequency of the little a, then any population will have a P and a Q value. And for a population that has only two alleles at this locus, P plus Q will always equal 1. They have to add up to unity. Okay, what we'll see in this population, however, is that we do not observe P squared, big A, we do not observe 2PQ heterozygotes, and we do not observe Q squared, little a individuals. This population has genotype frequencies that cannot be predicted based on allele frequencies alone. Let's just work this out. So what is P for this population here? Well, it's the frequency of the big A class plus 1/2 of the frequency of the heterozygous class. There's 1,000 individuals in this population, just to simplify the math. So we have 0.48 as the frequency for the big A individuals, and then 1/2 of the frequency of this, which is 0.5. So this is 0.48 plus 0.25. Got my calculator here just to help me do the math quickly, to make sure I don't make a mistake. So that's 0.73. So for this population, P is equal to 0.73. And Q, similarly, is going to be 0.25, so 1/2 of the frequency of the heterozygous class, plus 0.02, which is equal to 0.27. And those two, as we expect, add up to 1. Now, you can use P plus Q equals 1 as a way to determine Q, as opposed to just determining it based on frequencies. But if you've made a mistake in the first part and haven't calculated P correctly, then you won't calculate Q correctly by using that method. So it's a good way to check. I always use the frequencies, or counting up alleles as we did in the previous video, to determine P and Q, and then I check to make sure that they add up to 1. So here's what we mean about this population not being in Hardy-Weinberg equilibrium. This population has a P value of 0.73, so we expect P squared, big A individuals. So P squared in this case would be 0.73 squared. Okay, which is going to be 0.05329. So we would expect in this population to observe 0.5329 individuals that are big A, yet we see 0.48. These two don't match, and that's indicative of a population that is not in Hardy-Weinberg equilibrium. We would also expect 2PQ for the heterozygotes. So that's 2 times 0.27 times 0.73. That comes out to 0.3942. Okay, we would expect that many heterozygotes, and yet we don't see that. We have 0.5 for heterozygotes in this population. And last but not least, we would expect Q squared, little a. So that's going to be 0.27 squared, which would be 0.0729 is what we would expect. And yet we see 0.02. So what we have here is a distribution of genotypes in this population that cannot be determined or predicted directly from the allele frequencies. The allele frequencies are not distributed into genotype frequencies in the manner that we would expect. So something is throwing this population out of Hardy-Weinberg equilibrium. Perhaps it's non-random mating. Perhaps it's a fitness issue. Perhaps one of these genotypes, we see far fewer of these, for example, than we would predict. We predict that we would see about 0.07. We only see we only see 0.02 of those. So it might be that there's a selection issue that's removing some of these individuals from the population. Something in this population is not allowing it to be in Hardy-Weinberg equilibrium where we can directly predict genotype frequencies based on allele frequencies alone. One of the things that you'll have to become familiar with in working with questions is assessing whether or not a population is in Hardy-Weinberg equilibrium or not. And the way to do that is to calculate the P and the Q values from the population and then determine what you would expect for the different genotypes based on the Hardy-Weinberg distribution. If it matches the Hardy-Weinberg distribution, if what you expect is also what you observe, then it's in Hardy-Weinberg equilibrium. If these values do not match what you would predict using allele frequencies, then it's not in Hardy-Weinberg equilibrium.